Lesson 32, quotient theorem for square roots, congruency, and congruent triangles. At this point in your illustrious career of doing math, you have seen things written like that. You guys have done square roots? I hear some nodding, some I think I've seen that before. Not really sure. If I say that I've done it, does that mean you're going to go really fast? So no, I haven't. Anyway, that can be switched to the square root of 3 over the square root of 2. Okay? That is called the quotient. How do you spell quotient?
Quotient
of square roots. If you're from the Midwest, you'd call those roots. If you're from the South, you'd call them roots. And if you're around the creek, you'd be saying there's roots by the creek.
Actually, there's no difference between a creek and a creek. A creek usually has like tires or rusty metal near it,
That is a good
and
point.
they're usually slightly smaller.
Yeah,
Creeks have fish in them, and creeks kind of
the fish are dead. Okay, so when you break this down into the square root of the numerator over the square root of the denominator, it's called a quotient of square roots because that sign there, this long sign here, is not a fractional symbol. It's a division symbol. So it's the square root of 3 divided by the square root of 2. One of the things that you learn in math, in Algebra 2 and in pre-calculus, is that you do not want a radical sign in the denominator. Now once you get into calculus, you don't have to follow rules. That's what the
I have a question.
calc students say. It's, oh wow, we don't have to follow these rules anymore. Yeah.
Why can't we have a radical in the denominator?
Just like 2 over 4, you reduce to 1/2. It's the same thing. It's not wrong. It's just not their mathematician's favorite way of leaving an answer. Okay, so because we don't want a radical in the denominator, we have to get rid of the radical sign. And one of the things that we've discovered, not we, they have discovered, I didn't pay any attention to this, is that if you multiply a square root by itself, you get the square root of 9, which is the same as 3. So notice what happens. If we multiply the square root of 3 by the square root of 3, the radical sign disappears. So for this one here, they thought, if I multiply this by the square root of 2, then the radical sign disappears. But what's the problem with that? Okay, so give me the y. You have to multiply it by the top as well as the bottom.
Because then it wouldn't be the same equation, it would be the same.
Okay, what is any number over itself? 1. So actually what I'm doing is multiplying the square root of 3 over the square root of 2 times 1. And the identity property says anytime you multiply something times 1, you get itself. So I didn't change the value by multiplying it by 1. It just doesn't look like 1. It's the square root of 2 over the square root of 2. Okay, so that being the case, I get the square root of 3 times the square root of 2. My numerators, I multiply those, and what do I get when you multiply those?
Square root of 6.
Square root of 6 over 2. Can you reduce the square root of 6?
No.
Might you be able to reduce a square root on that numerator down the road somehow?
Yeah.
Okay, not necessarily in this one, but I mean, if you got the square root of 12 on top, you could reduce that. All right, so that is the direction we're going. So when they start giving you problems, they'll be doing this. They'll be giving you those. What do you know as far as adding and subtracting fractions? What's the first step? What was that? Common denominator. Okay. When you're dealing with radicals, you cannot do common denominators yet because how do you find the common denominator of the square root of 5 and the square root of 2? Okay. That is one of the key reasons why you want to get rid of the denominator or get rid of the radical in the denominator, is because it makes it a lot more difficult to add and subtract fractions if that radical is down there, because now you're trying to find common denominators that are radicals. So, a good reason to reduce. So let's change this. That. Okay. Makes it a little more doable. At least I have my radicals separated. Then I take each term and get rid of the radical in the bottom. So square root of 2 over square root of 5 times square root of 5 over square root of 5 plus square root of 5 over square root of 2 times square root of 2 over square root of 2. Multiply those out, and I get the square root of what?
10
Over?
square root of 5.
And the top here?
Square root of 10.
Over?
2.
2. So now that my radicals are gone, I can find common denominators. And my common denominator of 5 and 2 is what?
10.
So I change this to a 10. What do I have to do to the top? Multiply it by 2. Notice there's an assumed 1 up there. 1/5, 2/10, which is the same as 1/5, so you know you're okay. I'm going to change this denominator also to a 10. What number goes in front of my square root of 10? A 5.
Why did the denominator change?
Common
Common
denominator.
snap.
Okay.
7. Now you
Can
add
I, wait a minute guys, can I add my numerators?
Yeah.
Why can I add my numerators? What gives you the authority to be able to do that?
The same numbers underneath the radical.
The same numbers underneath the radical. There's one other thing that has to be true before you add. Yes?
Denominator.
Okay, the denominator has to be the same. One more thing that has to be true that you might not have dealt with yet. The index has to be the same. Anybody have any idea what an index is?
No.
Have you ever seen a square root sign with a 2 in there? Okay. What that means is you're taking the square root, what number times itself gives me 9, and you would say 3. So a square root sign always has a 2 there. They just don't put it there because you know that you're looking for 2. This is just telling you how many numbers you're looking for. I'm looking for 2 numbers multiplied together that give me 9.
So if it was a 3 and it was 27 cubed.
So, if this was a 3, and that was a 27, what number multiplied by itself 3 times gives me 27? So it need to be 3. 3 times 3 is 9, times 3 is 27. And there's 4th, 5th, I mean you can have 187 in there. So, and your calculator will do those. You aren't going to be able to do those. I mean, I used to teach, back when I was teaching Zach's mom math when she was a little punk, I was teaching them how to find the square root of like 6.24 by hand. And it would take literally 2 to 3 sheets of paper.
Really?
Find one.
Yeah. To
I hope
find
you
one square root. I don't do that anymore.
You would
just
only
because-
like assign them one problem, right?
Yeah. We
Okay,
didn't-
I'm like, if you assigned a whole
1 through
lesson.
30, go.
Yeah. Oh, 1 to 30 odds. You only have
Just find out
15 to do. So when you come back to school tomorrow with 45 sheets of paper for those 15 problems.
I'm not going to grade it.
Yeah.
Let's just count how many papers you have.
45 times
All right.
18 people.
So you end up adding, and you get 7 square root of 10 over 10. Treat the radical kind of like you do a variable. 7x plus 2x is going to give you 9x. 7 times the square root of 10 plus 2 square root of 10, 9 square root of 10. So when you add and subtract, pretend like they're a variable, and then you'll be okay. Okay. 3 times the square root of 3 over 7 minus 5 square root of 7 over 3. Anybody have any first step ideas for me? I'm sorry?
Simplify the radicals.
Okay, I'm going to simplify the radical. How am I going to do that? See if we have make sure we're on the same page here, what you mean by simplify the radical. We're going to do something with the radical. Kendra?
You move the 3 to the top with the square root of 3. And so you make it 3 square root of 3 over 7.
Okay, so you're going to do that.
Yes.
Okay, so that has to do with the simplifying that Kelsey had brought up. Okay, now what? Okay, I'm going to times my first denominator by what, Erica? Okay, and I'm going to multiply the second radical by what? Okay. Once I do that, what do I do with this first term over here?
We'll make it 3 square root of 7. I don't know.
What do I do with my square root of 3 and my square root of 7?
3 square root of 21.
3 square root of 21. Can I do that?
Yes.
Can I multiply those?
Yeah.
I can multiply anytime there's multiplication, I can pretty much do it. Okay, so what do I get for the second mess?
5 square root of 21.
Over?
3.
Okay, so now can I subtract?
No.
No. What's the problem, Zach? Okay, the denominators aren't the same. So now I have to work on that step. So what is the common denominator of 7 and 3?
21.
21. So we're going to change that to a 21. And what are we going to change this 3 to?
No.
Am I going to change it to? 9. Why are you going to change it to 9, Seth?
Multiplied 7 by 3, so you multiplied it.
3 times.
The top number.
Thank you, Seth. All right, so we have 21 under the 3. We're going to change the 5 to what? For the same reason. We multiplied the 3 times 7 to make it 21. We have to multiply the 5 times 7.
Exactly.
Okay. So 9 minus 35 is?
Negative 26.
Negative 26 over?
21.
21. Can that reduce?
No.
How would you know whether 26 over 21 can reduce or not?
One's odd versus even.
Okay, one's odd and one's even, but doesn't
No.
25 and 10? 26 and 21. What are my factors of 21? Does either one of those go into 26? No, just 2 and 13. So I'm done.
The normal way you
All right.
I have a quick question.
Yes.
So if you say the 26 was 9 and the bottom one was a 3, would you be able to simplify them? Because
Yes.
even though there's a radical beside the 9?
Yep. Because all you care about is the numbers that aren't in the radical sign. So you compare radical to radical, whole number to whole number, and you're all right. Good question, Erica. Okay, so congruency. Anybody know the difference between congruency and equality? Has anybody ever taught you the difference between the two? Kendra?
Congruent, just like they're similar to each other, and then equal. Equality is the same.
Okay, pretty close. Equality deals with just numbers. 4 equals 4. Geometric equality, like what Kendra was saying, as far as figures are concerned, they're geometrically equal in size, Anytime you got something, a geometric shape, it's always congruent, never equal. Now the measurement of the angle could be equal to the measurement of another angle because those are numbers that you're comparing, and numbers can equal numbers. But objects cannot equal objects because this object and this object are not the same object, whereas 4 and 4 are the same number. So it works as far as that is concerned. I don't really get into making a real huge deal over semantics, whether you use congruency or equality interchangeably. I don't really care. I know what you mean. But that's kind of what this section goes into a little bit. It's a couple of the words that they use in here, guys, is reflection, translation, and rotation. You guys used all three of those before?
Yeah.
Okay, so if I have an angle here, and I have an angle here, to get from here to here, which of those three would you say would most easily describe what I just did? A rotation. We've got a point here when you have a rotation, and you are, whoops, I've got my triangle wrong. Didn't somebody catch that? Yeah, guys. Okay, so we've got a point here that this thing here rotates around to give me that.
That was cool. I like that too.
Okay. If I have this here and this here, that would be a translation. Translation means that you move something left or right and then up or down or both. So I kind of moved this over here and then down. So maybe over 5, down 6 to get there. So that would be translation. Reflection then means that, come on, it's kind of like a whole mirror thing where you have this here, and then you have a reflection line, and then you have the same object reflected like a mirror, but bigger. Yeah.
Do you need the reflection line?
I'm sorry?
Do you need the
You do
reflection
need a
line?
reflection line because the distance between the line and the object has to be the same.
And the reflection line could be this way.
It could be, yeah, the reflection line could be any direction.
Oh, yeah. I was just
But
wondering
it's just,
for
it's like
idea.
taking it here and flipping it over. So that's what a reflection is.
And we're done.
Okay.
Yeah, we are. Right? Yeah, we're done.
All right, so I do have an extra credit. Let me turn this off here.